Black hole thermodynamics and the information paradox, a deep dive into the mysteries of the universe. The study of black holes has long been a cornerstone of theoretical physics, offering profound insights into the nature of space-time, gravity, and quantum mechanics. Among the most intriguing and challenging aspects of black hole physics are the laws of black hole thermodynamics and the infamous information paradox. These topics not only push the boundaries of our understanding of the universe, but also force us to confront fundamental questions about the nature of reality itself. This exploration delves into the intricate relationship between black hole thermodynamics and the information paradox, examining their historical development, theoretical underpinnings, and the ongoing debates that continue to shape modern physics. The birth of black hole thermodynamics. The story of black hole thermodynamics begins in the early 1970s, when physicists began to notice striking analogies between the laws governing black holes and the laws of thermodynamics. The first hint of this connection came from the work of Jacob Bekenstein and Stephen Hawking. Bekenstein proposed that black holes possess entropy, a measure of disorder, which is proportional to the area of their event horizons. This was a radical idea at the time, as entropy was only traditionally associated with the number of microscopic states of a system, and it was unclear what microscopic states a black hole could have. Hawking, initially skeptical of Bekenstein's proposal, soon made a groundbreaking discovery that would cement the connection between black holes and thermodynamics. In 1974, Hawking showed that a black hole was not entirely black. They emit radiation due to quantum effects near the event horizon. This phenomenon, now known as Hawking radiation, implies that black holes have a temperature and can radiate energy, much like a hot body. Hawking's calculation revealed that the temperature of a black hole is inversely proportional to its mass, meaning that smaller black holes are hotter and radiate more intensely than larger ones. With the discovery of Hawking radiation, the analogy between black holes and thermodynamics became undeniable. The four laws of black hole mechanics formulated by Barrandine, Carter, and Hawking closely mirror the four laws of thermodynamics. The zeroth law states that the surface gravity of a stationary black hole is constant over the event horizon, analogous to the zeroth law of thermodynamics, which states that temperature is in constant thermal equilibrium. The first law relates the changes in mass of a black hole to changes in its area, angular momentum, and charge, similar to the first law of thermodynamics, which relates change in energy to work and heat. The second law, often referred to as generalized second law of thermodynamics, states that the total entropy of a system, including the black hole's entropy, never decreases. Finally, the third law states that it is impossible to reduce the surface gravity of a black hole to zero through a finite number of processes, analogous to the third law of thermodynamics, which states that it is impossible to reach absolute zero temperature. The information paradox, a crisis in physics. While black hole thermodynamics provided a beautiful and consistent framework for understanding black holes, it also gave rise to one of the most profound puzzles in theoretical physics, the information paradox. The paradox arises from a combination of quantum mechanics and general relativity, two of the most successful theories in physics, which nevertheless seem to be fundamentally incompatible when it comes to black holes. The crux of the information paradox lies in the fate of information that falls into a black hole. According to classical general relativity, anything that crosses the event horizon of a black hole is irretrievably lost to the outside universe. The event horizon acts as a one-way membrane, and no information about the interior of a black hole can escape. However, quantum mechanics insists that the information cannot be destroyed. It must be preserved in some other form. This principle is encapsulated in the unitarity of quantum evolution, which guarantees that the information about the initial state of a system can always be recovered from its final state. Hawking radiation complicates this picture. As a black hole radiates, it loses mass and eventually evaporates completely. If the information that fell into a black hole is irretrievably lost, then the final state of the radiation will be a mixed state, with no memory of the initial state of matter that formed the black hole. This would violate the principle of unitarity and imply a fundamental loss of information, which is incompatible with quantum mechanics. The information paradox has led to a crisis in physics, as it suggests that our current understanding of quantum mechanics and general relativity is incomplete. Resolving the paradox requires a deeper theory that can reconcile these two frameworks, often referred to as quantum gravity. Several approaches have been proposed to address the paradox, each with its own strengths and challenges. Approaches to resolving the information paradox. One of the earliest and most influential approaches to resolving the information paradox is the idea of black hole complementarity. Proposed by Leonard Susskind and others, black hole complementarity suggests that information is both reflected at the event horizon and passes through it, depending on the observer's perspective. From the perspective of an outside observer, information is encoded into the Hawking radiation and never actually enters the black hole. From the perspective of an infalling observer, however, the information crosses the event horizon and is lost to the outside universe. This duality is reminiscent of the wave-particle duality in quantum mechanics, where particles can exhibit both wave-like and particle-like behavior depending on how they are observed. Another prominent approach is the holographic principle, which posits that all the information contained within a volume of space can be represented as a hologram on the boundary of that space. This idea was inspired by the discovery that entropy of a black hole is proportional to the area of its event horizon, rather than its volume, suggesting that information content of a black hole is encoded on its surface. The holographic principle has been formalized in the ADS/CFT correspondence and conjectured duality between a type of string theory in a high-dimensional space. As can formal field theory and the boundary of that space, the ADS/CFT correspondence provides a concrete realization of the holographic principle and offers a potential resolution to that information paradox by suggesting that information is never truly lost in a black hole, but is instead encoded into the radiation and the boundary theory. More recently, the firewall hypothesis has emerged as a radical proposal to resolve the information paradox. The firewall hypothesis suggests that an infalling observer would encounter a high-energy firewall at the event horizon, rather than smoothly crossing it. This firewall would destroy any information about the infalling matter, effectively resolving the paradox by ensuring that information is not lost, but instead scrambled and radiated away. However, the firewall hypothesis is controversial, as it challenges the equivalence principle of general relativity, which states that observer in free fall should never detect any local effects of gravity. The role of quantum gravity. At the heart of the information paradox is the need for a theory of quantum gravity, which can unify quantum mechanics and general relativity. Several candidate theories of quantum gravity have been proposed, including string theory, loop quantum gravity, and causal dynamical triangulations. Each of these approaches offer a different perspective on the nature of space-time and the fate of information in black holes. String theory, for example, posits that fundamental particles are not point-like, but are instead one-dimensional strings that vibrate at different frequencies. In the context of black holes, string theory suggests that the information about infalling matter is stored in the vibration of these strings, which are then eradicated away as Hawking radiation. The ADS/CFT correspondence, a key result in string theory, provides a concrete framework for understanding how information is preserved in black hole evaporation. Loop quantum gravity, on the other hand, attempts to quantize space-time itself, suggesting that space-time is composed of discrete loops that interact to form a network. In this framework, the information paradox might be resolved by the discrete nature of space-time and Planck's scale, which could prevent the formation of a true singularity and allow for information to escape from a black hole. Causal dynamical triangulations offer yet another approach, proposing that space-time emerges from a statistical ensemble of discrete geometries. In this view, the information paradox might be resolved by the probabilistic nature of space-time, which could allow information to be preserved in a way that is not apparent in classical general relativity. The future of black hole thermodynamics and the information paradox. The study of black hole thermodynamics and the information paradox continues to be a vibrant and active area of research, with new insights and challenges emerging regularly. The development of quantum gravity theories, the exploration of holography, and the ongoing debate of the Farrell hypothesis are just a few of many avenues being pursued by physicists. One of the most exciting recent developments is the use of quantum information theory to study black holes. Quantum information theory provides powerful tools to understanding how information is encoded, transmitted, and processed by quantum systems. By applying these tools to black holes, physicists hope to gain a deeper understanding of the information paradox and the nature of quantum gravity. Another promising direction is the study of black holes in higher dimensions. In theories with extra spatial dimensions, such as string theory, black holes can have very different properties than in four-dimensional space. For example, high-dimensional black holes can have more complex event horizons and can have new types of instabilities. Studying these black holes could provide new insights into the information paradox and the nature of quantum gravity. Finally, the advent of gravitational wave astronomy has opened up new possibilities for testing the predictions of black hole thermodynamics and the information paradox. The information of gravitational waves from merging black holes by the LIGO and the Virgo collaborations have provided direct evidence for the existence of black holes and has allowed physicists to test general relativity in the strong field regime. Future observations of gravitational waves from black hole mergers, as well as other astrophysical resources, could provide further clues about the nature of black holes and the fate of information. To conclude, black hole thermodynamics and the information paradox represent some of the most profound and challenging problems in modern physics. They force us to confront fundamental questions about the nature of space-time, gravity, and quantum mechanics, and they push the boundaries of our understanding of the universe. While significant progress has been made in the understanding of these issues, many questions remain unanswered, and the search for a complete theory of quantum gravity continues. The study of black holes is not just an academic exercise. It is a journey into the deepest mysteries of the universe. As we continue to explore these mysteries, we are all reminded by the words of John Archibald Wheeler, who famously said, "Black holes teach us that space can be crumpled like a piece of paper into an infinitesimal dot, that time can be extinguished like a blown-out flame, and that the laws of physics were regarded as sacred and immutable are anything but." In the quest to understand black holes, we are not only uncovering the secrets of the cosmos, but also redefining our understanding of reality itself.